Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the hydraulic systems on the Boeing 737. So in this we'll be covering the reservoirs and their pressurization, the fluid, the pumps, pressure modules, fuses and filters, indications, the services supplied, and redundancy. As always, please treat your company training and their manuals as the authoritative source information. Okay, a quick word about my previous presentation, the wheel well hydraulics tour. If you haven't already watched this one, then I recommend that you do before watching this video. It will help. It's only about a 10-minute video, and it hopefully just puts some of the components into context for you, where they are in the wheel well and how they interconnect. I'll be going through all of those components in more detail in this presentation, but think of the hydraulics tour video as like a kind of intro or just a scene setter for the hydraulics visible in the wheel well. Okay, if you're still with me, one thing I should have mentioned, perhaps in that wheel well hydraulics tour, but didn't, is that all the hydraulic pipes have got this blue and yellow identification tag. You can see it on obviously the pipe at the front, but there are two behind in shot as well, just out of focus. Now all the pipes will have that. It will help you if you wish to, go into the wheel well and see some of these things that I'm mentioning. You can follow the systems through yourself. Many, but not all of the pipes also have a named label to the right of the identification. So this one in shot here shows B system pressure with a flow arrow to the left of picture. They don't all have that named arrow, but a lot do. So you can actually go to a random hydraulic pipe, find its label, and it will tell you hopefully what service it supplies, which just helps you build up a mental model of where everything is and how it all fits together. Okay, so on with the presentation. So here we have the almost obligatory schematic for a complex system. This is the schematic that I use for hydraulics. You've got one in your FCOMs. The engineers have got several in their maintenance manuals, and they all look different. They're all laid out differently, but of course the functionality of them all is all hopefully identical. You just use whichever one you feel comfortable, either mine or the FCOM one or any others you can see issued by third parties. They all should be the same. It's whichever one sits right with yourself. The obvious thing to say about this schematic, like probably all of them, is that at first sight it looks very complicated. I can assure you it isn't. It's just that there's a heck of a lot in it. That's all it is. Like all schematics, when you break them down into their individual components, they're actually quite straightforward, and that's what I'll be doing in this presentation, taking you through it step by step so that you can build it up and understand how the hydraulic system fits together. All right, on with the show. We'll start at the beginning with the reservoirs. There are two main hydraulic reservoirs, A and B, and these are pressurized to around about 47 psi from the pneumatic system. And the reason for that is to prevent foaming of the fluid and also ensure that a positive flow of fluid reaches the pumps. Now, this foaming phenomenon, for those of you that haven't seen it before or heard of it before, It happens in all liquids when you reduce the pressure, particularly if you reduce the pressure quite quickly. And the demo I usually give to guys who aren't familiar with this is if you have a bottle of water, still water that you might drink in flight. So on the ground, make sure the lid's screwed on nice and tightly. You take off, you climb, you get to top of climb, pull out the bottle of water, and then open the lid. And you will see in that bottle of water lots of little air bubbles form. That's foaming, and it happens just the same as it did to your bottle of water. It will happen with the hydraulic fluid if you don't put a head of pressure on it. And it also happens with the fuel as well, which again is part of the reason why we have had the fuel pumps. Any liquid that's depressurized quickly or relatively quickly, you will see that effect happen. So that's the reason for pressurization. I'll say they pressurize it to about 47 psi, but as you can see in the photo there up at the top right, each reservoir's got a pressure relief valve set at 60 psi. So if by any chance it's over pressurized, then the excess pressure will vent out there. Now this pressurization comes, if you remember from the pneumatics presentation I gave you, it actually comes for the B system from the right pneumatic duct, and from the A system from the left pneumatic duct. And you can see the lines there on the photo coming up the forward wheel well wall, taking that air pressure from the duct to the top of the reservoir. Now, after having introduced this video showing you the pipe labeling for hydraulic pipes, the first pipes we're going to look at here are actually not hydraulic pipes; they're compressed gas pipes, because it's so you can find those quite easily in the wheel well, because some of the very few pipes in the wheel well which have got the compressed gas label on them. So next time you're on a walk around, you can go in the wheel well and just trace it up and see it. Also up there is a balance line to the A reservoir. So this interconnects the two reservoirs to equalize their pressures. There is a vent line that I've already mentioned from the pressure relief valves between both reservoirs. This takes any overpressure fluid residue across the wheel well ceiling, then down into a drain mast, which is located behind the wheel well. This also prevents fluid backflow into the pneumatic system. The vent line going across the ceiling of the wheel well is quite easy to spot, because it's quite a thick pipe, and it's the only diagonal running pipe across there. If you're unsure of this, again, refer back to the wheel well video I did. The drain is also shared by the APU shroud drain as well, which is why there are two pipes going into it. Not all airlines label the drain shroud, which is why I've shown a photo of one operator that I flew for that did. Some actually even only label it as the APU shroud drain, but the hydraulic reservoir is connected to it, as you can see from inside the wheel well. Alright, so we've seen the B system side of the reservoir. This is the A system side. Again, it's got a pressure relief valve on it, and the other side of that, the air pressure goes to the top of the reservoir. You can see the reservoir pressurization line coming from, which you can follow down the wheel well wall to the left pneumatic duct. And again, you can see the left-hand side of the balance line that comes from the B reservoir. There is a T junction in that balance line, which you can see going down there, and that goes to a manifold assembly, which is here if you follow the line down. Now this manifold assembly it's used by engineers to manually pressurize the reservoirs using an external ground air source, which plugs into that yellow charging valve there. And they do this when they need to when they need to use the hydraulics, but don't have a bleed air source. So they've either, say for instance it's in the hangar and they don't want to, either run the engines or the APU, or the APU maybe isn't even fitted. That's away on maintenance as well. So they can pressurize the reservoirs here, which is why there's a reservoir pressurization gauge in the in the wheel well, so they can see what level to pressurize it up to. So that line there goes up to join the balance line between the two reservoirs with external air. All right, so this is now just a short video of the 737 NG wheel well, showing the reservoir pressurization lines, and I include this because the wheel well hydraulic tour I did, I actually filmed it on a Classic, and these components are different. It's actually the only real difference between the Classics and the NGs hydraulically. It shows the B system reservoir pressurization run from the pneumatic manifold to the reservoir, across the balance line, and then down to the charging valve. On the Classics, where the manifold assembly is on the NG and the Max, they've got this unit called the reservoir pressurization module. So I say you won't see this on an NG or a Max. This takes the external, the pneumatic sources, left, right duct or external, into a pressurization module, then separates the air for the A and B reservoirs. That air then goes through two depressurization valves, which are sat on top of the module. They're labelled, and then onto the reservoirs. There's no balance line on the Classics because this unit effectively does the same as what the balance line would. Now, if you look in the wheel well, you may see either one or two reservoir pressurization gauges, and that tells you whether the hydraulic reservoir pressurization system has been modified or not. From 2003, there was a modification available which fixed two problems. The first one was hydraulic vapors getting into the flight deck caused by hydraulic fluid, leaking up the reservoir pressurization line back to the manifold, giving hydraulic fumes in the air conditioning. And the second one was getting a hydraulic pump low pressure light during very long flights in a cold soaked aircraft. This was caused by water vapor condensing in the line, in the reservoir pressurization line, and that would then freeze during a long flight due to the cold soaking and block the reservoir bleed air supply. So if you haven't got a reservoir bleed air supply, as we've just seen from reservoir pressurization, you'll get the foaming, you won't get the header pressure to the pumps, and you could, in extremis, lose hydraulic pressure. So that's why the mod was done. If your aircraft is unmodified, you will see two reservoir pressurization gauges, one for the A reservoir and one for the B reservoir, like in the upper photo. If your aircraft has been modified, you'll only see one reservoir pressurization gauge, and that's just labeled reservoir pressure. All right, onto the Onto the reservoir itself. This particular one is the A system reservoir, and this photo was actually taken on a Max, so it's got the nice shiny new green reservoir there. So working from the top to the bottom, the green pipe running across, that's your vent line to the drain mast, the one that runs diagonally across the ceiling of the wheel well. Below that, we've got the balance line going across to the B reservoir, and below that in green you've got the pressurization line coming up from the left pneumatic manifold. On the side of the reservoir, you've got the quantity gauge and a transmitter which goes to us in the flight deck, giving us our hydraulic quantity. The reservoir itself, 21.6 a litre is the full level. The actual capacity of it is slightly greater than that because obviously it's not entirely filled with fluid, so you've got the air pressure at the top. It's 2/3 of the size of the B system reservoir. Coming out to the bottom, you've got two pipes there, one to each pump, the engine pump and the electric pump, and above it, the silver braided pipe going into the side of the reservoir, that's your fluid return line. So that's where the fluid, after it's been round the aircraft services, that's where it comes back and is put back into the reservoir. The B system reservoir is very similar. This one's in white, so it's an NG. At the top again, you've got the line from the right pneumatic manifold. You've got the reservoir pressurization and vent line just about visible above the reservoir itself. Again, you've got the gauge and the transmitter. The first pipe going into the reservoir on the left-hand side there, the upper one with the red elbow, that's refill fluid from the standby reservoir. The hydraulic fluid is actually replenished for the B system. It's replenished through the standby reservoir, and that's the interconnecting balance line between the two. I'll say the B system's capacity is 31.1 litres, which is half as big again as the A system. The fluid return line is the next one down, with the gold coloured fitting at the top of it, and at the bottom you've unlike the A system, you've got three pipes coming out of it, the extra one being for the PTU. On the originals, for anybody still flying them, and by originals I mean the 1 and 200 series, the B system reservoir was very small. It was actually just under 6 litres, so that's about a sixth of the size of the current B reservoir on the NG and the Max. On the originals, the A system was used both for the flaps and the landing gear, so B was effectively just a backup hydraulic system for the other services. A was the one that was the major system. The standby reservoir. This is a photo of the unit on the NG and the Max. Differences between the other ones is it's kept full, absolutely full of fluid, so it doesn't contain any air, so it doesn't need pneumatically pressurizing, which keeps the system quite simple. The fluid is kept pressurized by a fluid filled balance line to the B system, which I mentioned in the previous slide. So going through the components on this, then from top to bottom, you've got a low quantity switch on the very top that comes on at 50%. The balance line is there from the top, but goes to the B reservoir. The capacity of this reservoir, just over 13 litres. And the fluid is refilled on that line which goes into the center of it on the right of the picture. Output of fluid is the large braided line down at the bottom, and fluid is returned along that thin green line which goes back in on the other side, which you can't see in this photo. But you can see it in this photo. This is a photo of the standby reservoir and the classics. All the components are the same as the NG and the Max. Just on this photo, you can see the fluid return line because it goes in at the back. The real difference between the classics and the NG, apart from the shape, the capacity is actually the same. To within a few mil, the same. The difference is the standby hydraulic pump is in the wheel well here on the classics, whereas on the NG and the Max it's moved out. On the originals, the standby reservoir is smaller again at 7.2 litres, so it's around about half the capacity of the reservoirs on the classics onwards. But again, all the components there are absolutely the same as they are even on the Max today. Servicing of the reservoirs. The hydraulic fluid, it's replenished with this sort of wand and hand pump arrangement, which you can see in the right hand wheel well. If you just look over the lip of the of where the wheel goes, you'll see it down there. The hand pump's that white handle that's bracketed into the full bulkhead. If you look above that, you'll see a 3-position switch, or selector switch for either A, B, or closed. Remembering that B actually replenishes the standby reservoir and then sends the fluid onto the B reservoir. For those that are interested, the official specification of the hydraulic fluid, it's a fire-resistant version known as BMS 3-11 Type 4. Common brand name for this is Skydroll, and that's usually what it's referred to as. Other brands are available. And this stuff isn't cheap. I googled it just before I did this presentation just to get an idea of price. And it's about $1,000 for a case of 24 quarts. So not cheap stuff. Alright, so inside the reservoirs you've got standpipes. Now this data is only applicable for the NG and the Max. On the classics, the standpipes are a slightly different height and arrangement. So this information is just for the NG and the Max. So the A system's got a standby on the engine-driven pump line. If you get a leak in that engine-driven pump or any of its lines, the fluid will drain away, but only to the level of that EDP standpipe. So that will leave enough fluid for continued operation of the electric pump. Now, if there's a leak in the electric pump or any of its lines, then you just lose a system fluid. There's no reason for a second standpipe at all. The B system, and again, this is only applicable for the NG and the Max. It's got a much shorter standpipe because it only needs to be shorter, because the only system this could feed in the event of a leak would be the PTU. That's because the engine-driven pump and the electric pump are on the same feed from the reservoir. So if there's a leak in either the engine or electric-driven pumps or any of their lines, the quantity will disappear away to indicate 0. Now, although it's indicating 0, there is enough fluid for PTU operation. So it's not really 0, but that's the indications we get in the flight deck. The standby system, and this is applicable for all generations of 737, the standby reservoir doesn't have a standpipe. If there's any leak in the standby pump or any of its lines, the standby system will be lost. Now, the manuals say that although the standby reservoir is connected to the B system reservoir, a leak in the B system will not affect operation of the standby system, which is comforting to know. And just a reminder, the low quantity light, which is on the flight controls panel, that will illuminate at 50%. So to summarize all of that, on the A system, there are separate standpipes for the engine pump and electric pump. A leak in the engine-driven pump or any of its lines will leave enough for the electric pump operation. For the standby system, a leak in the B will not affect operation of the standby system. And on the B reservoir, you've got a direct feed to the PTU. There's a combined standpipe for the engine and electric pumps, which is a difference from the classics, but it's still enough for PTU operation. Alright, so hydraulic quantities. The table I've drawn up there, and I've had to collate this from a myriad of sources to get this in all one place. But it shows that the nominal quantities at different levels in the reservoirs. So this shows all the standpipe levels for all of the reservoirs for all of the generations of 737. So you can, just only need to memorize the one on the version you fly. But how you'd use this, I guess, is if you're in a 737 NG and you notice the A system quantity dropped to 20%, then you can suspect a leak in the engine-driven pump or its lines. What you choose to do with that information is, of course, up to you, but it's all good background knowledge, and you never know. There could be a situation where this knowledge may be useful. All right, that's enough of the reservoirs and the fluids. Let's go on to pumps now. I'll just start briefly with the originals. I realise that there are very few people watching this who fly them, but just for a kind of historical perspective, and help to show you the derivation of where we got the present arrangement today. The classics had System A, which remember was the primary system, powered by the two engine-driven pumps. Which probably come as quite a surprise to those of us still flying later generations. The system B was powered by electric pumps, so this is completely different to the way we have it today. The ground interconnect switch up there, that just allows the system B electric pumps to pressurize system A when you're on the ground with the parking brake set and the engine's not running. And that's really just used by engineers to pressurize the A system without having to start up an engine. Okay, so back into the present day. From the 737-300 onwards, each hydraulic system, as we know, has got both an engine and an electric pump, power from the opposite side, either gen bus on the classics or the transfer bus on the NG and the Max. This is for greater redundancy in the event of an engine or generator failure. The engine-driven pumps are by far and away the most powerful. They've got a hydraulic flow rate of 37 gallons per minute, or 22 gallons per minute on the classics, whereas the electric pumps only produce 6 gallons per minute. So the engine-driven pumps are 6 times more powerful. The standby pump, which you remember is activated from the flight controls panel, is even less at 3.7 gallons per minute. But then again, it has a lot less to do. So let's have a look at those engine-driven pumps. They are on the accessory gearbox, which is on the left-hand side of the engine. And the thing about these is they are always running. Whenever the engine's running, the engine-driven pumps are running. Unlike the generators, which you can see above in this photo, they can't be disconnected. There is no red disconnect switch like there is for the Jennies. Now we know there's an on-off switch, but that is actually kind of something of a misnomer. When you switch an engine-driven pump off, the pump actually remains running, What you're doing by switching by moving the switch to off is you're energizing a solenoid operated blocking valve that blocks the pump output. So there's no output from the pump. The hydraulic fluid still flows around the pump case, but that's for cooling, because obviously the thing's still turning. But you cannot physically switch this pump off, which you may need to bear in mind, and I'll come on to why later. Now, because the engine-driven pump solenoid-operated valves are energized when the pump switches are off, you should keep the engine-driven pump switches in the on position to prolong their life, and that's why, certainly in the flight deck, there's no procedure or no normal procedure for us to ever switch those pumps off. They remain on, sort of day in, day out, week in, week out. They're only ever really switched off by engineers for maintenance, or for us if we're following the QRH procedure, say for a low pressure. But that's why those switches are always kept in the on position. Now, when an engine fire switch is pulled, the engine pump supply shutoff valve in the wheel well shuts off the fluid to the engine driven pump and disarms the low pressure light. And that photo there in set is just me in the wheel well. This is still taken from the previous video, showing you where that valve is. I mean, I could have just shown you a picture of the valve, but it wouldn't mean much. So I just used that photo to kind of put it in context, and that kind of tells you that it's out there halfway to the pylon. So this is partly why it's important to pull a fire switch as directed by the QRH, of course, if you have engine damage. Because in doing so, what you're doing is you're stopping the fluid flow out to that engine-driven pump. Because remember that pump cannot be switched off. It'll always keep turning, and if it's always turning and there's damage in there, it could be just indefinitely leaking your hydraulic fluid out, which you might need for other services. So if you pull this fire switch as directed by the QRH, then it will stop hopefully stop the hemorrhaging of fluid out from the pump or the vicinity of the engine. Now, when you do this, it's probably worth noting that the electric pump is still available after a fire switch is pulled, so you haven't necessarily lost the A or B system, depending which side it was that you pulled. But of course, the output is going to be much slower than the engine-driven pump. Okay, so let's have a look now at the electric motor driven pumps, and these are located in the forward wall of the wheel well near the reservoirs. So next time you're on your walk around, you can go in and have a look at these. They're there on display for you. The pump output flows through that diagonally mounted cylinder, which is an acoustic filter, and that reduces the noise and the vibration, which is quite considerable. I mean, you'll know it makes quite a noise already if you do a walk around with either of the pumps on. But without that, it's very loud. From there, the fluid goes out to the System A pressure module. The fluid comes into the pump from the reservoir through that braided cable that you see on the right hand side of the pump. And the construction of the pump, the left hand side is actually the electric motor. I mean, you can see the three-phase wiring going into it there, and the right hand side is the pump. Okay, for cooling of these pumps, because these, particularly the electric one, does get very hot. All of the pumps, so the electric pumps, and the engine-driven pumps, all pumps, are cooled with some of the supply fluid. Th that's kind of diverted around the case of the pump, and then it comes out and goes to the case drain filter, which you can see on the bottom of the photograph there, and then onto the fuel fluid heat exchanger. So this fuel hydraulic heat exchanger, it's in there's one in each wing tank, near the wing root. And it's near the wing root because the dihedral of the wing keeps the fuel, near the wing root. It's the last place it'll be used from. So the heat exchanger will work on the lowest possible fuel quantity. There's one in each wing. System A is cooled from tank 1 and system B is cooled from tank 2. There is a limitation of minimum fuel for ground operation of the electric pumps of 760 kilos in the related tank, and this heat exchanger is the reason why for that limitation exists. It's only there for the limitation's only there for the electric pumps. It's actually not there for the engine-driven pumps, because the engine-driven pumps don't get as hot because they don't have the electric motor. I mean, the case drain fluid from the engine pumps does also go through the heat exchanger, but the limitation on minimum fuel isn't there. So talking of heat, let's have a look at what the pump overheat will where this kind of comes about. If an overheat is detected in either the electric pump itself or the electric pump case drain fluid, the overheat light will illuminate, and the trigger temperatures for that are there. They're around about 110 centigrade. Now this light will extinguish again below 85 if it cools below 85 C. Some electric pumps will auto shut off for an overheat, so check your FCOMs for which version you've got. Most of them don't actually. Most you have to go into QRH and manually switch off the electric pumps. You can see on the photo the two pickup points for the overheat sensors there. And again, I just make the point that the engine pumps don't have an overheat light. That's because there's no electric motor on them to heat up, so that they get less hot. Again, this is also why the minimum fuel limitation doesn't apply to running the engine-driven pumps. Okay, for the standby pump, as we've already mentioned on the originals and the classics, it's there on the keel beam. Again, like the other pumps, it's cooled by case drain fluid, which is then filtered, but then returned directly to the reservoir, so it doesn't go through the heat exchanger. You can see level. It's the large part of this pump is actually the motor. It's the motor that drives the pump. The pump is the small part on the right hand side. Supply fluid going in there on the braided line. On the NG and the Max, you won't find the standby hydraulic pump in the wheel well. It's been moved out onto the right aft wing body fairing behind the bulkhead. Also the brake accumulator has as well. I've never had a straight answer why this was done. I suspect it was because the landing gear was lengthened for the NG, and as a result the space on the keel beam got a bit tight, so the pump moved. It could also be to stop any secondary damage from, say, a tyre burst affecting the standby system. I don't know. I mean, either reason is valid. They had that empty space there in the wing body fairing, and in my opinion, that this is a big improvement to use it and put these critical components here. The only difference between this pump and the pump that was on the keel beam in the classics is that red horn on the far end of it, and that's a cooling air duct, because obviously there's less airflow in here than there would be in the wheel well. So the air comes in through that air inlet on the door. You can just see that grill at the bottom into there, cools the motor, and then the air is exhausted in the same place on the opposite side of the aircraft. So on the left aft wing body fairing, you will see another sort of hole, and you may wonder what it's for. Well, now you know. It's the exhaust for this cooling. All right, so standby pump control. Let's take a look at that. The standby hydraulic pump can be activated well in a number of ways, but manually we can activate it by moving either of the flight control switches to the standby rudder position, or by moving the alternate flap switch to arm. So any of those three switches will start the standby hydraulic pump, and you know you can do this safely, you know, on the ground, as long as there's no wire locking on your alternate flap switch, and certainly on the classics you can hear the pump run. On the NGs and Max it's more difficult to hear it because it's further aft and outside of the aircraft. The standby pump will also activate automatically through either the auto standby system, which I'll cover later, or the main rudder PCU force fight monitor, and I'll cover that on the flight controls videos. When the pump is activated for the first time in a while, so you know, several hours have passed since it's been activated, the low pressure light will illuminate for a second while the pump charges, and then that light will extinguish. So that's a little confidence check for you that the pump's actually running. The standby rudder on light will also illuminate for all activations with the exception of alternate flaps. So certainly moving the flight controls to standby rudder will bring it on, as will the auto standby system and an activation from the force fight monitor. Okay, so this is just a video demonstration of the alternate flap switch to arm and the flight control switch to standby rudder. Okay, I'm going to start with the alternate flap switch first. Just open the red guard, nothing happens. Move the switch to arm. Notice the low pressure light illuminates. This is just for a fraction of a second. I've paused the video here so you can see it. That's the proof that the standby hydraulic pump is energized. So the motor's got electric power and the pump has just primed itself, and when it's primed that light will extinguish. So we can continue it here and just close the guarded switch, go to the flight controls now, and I've got the A system off and the B system on. That's why the low pressure light's on the A system. Through to standby rudder light comes on, and the flight controls low pressure light goes off. Switch it off and it's back to normal. With the B system, through to standby rudder, again low pressure light is off as you would expect, and the standby rudder light comes on. That's it. So in summary, the engine-driven pump has got 6 times the output of the electric pump, so it's a much stronger pump. The fire switch, pulling the fire switch, it'll only shut off fluid to the engine-driven pump. The engine-driven pump cannot be switched off. And the electrical source for the electric pump is from the opposite side. Okay, pressure modules, fuses and filters now. So the outputs of the pumps go to the system pressure module, and there's one of these for each system. So A, B and standby, they've all got a pressure module. The one in the photo here is the B system module, but the A system looks pretty much identical. Now these clean, monitor and distribute the fluid pressure from each pump and protect the system from overpressure. So you can actually see in the photos you've got the feed into this. From the left you've got the feed from the the electric pump, and from the right you've got the feed in from the engine-driven pump. Actually, on the A system pressure module, those two are reversed because obviously the engine's out on the wing, it's outboard of the pump. But for the B system, it's as labelled. And you can see the pressure filters at the bottom, and then up at the top is the where the pressure is sensed from the each pressure module, and that's sent to us in the flight deck for triggers for low pressure warnings, or further up and to the left there, the actual pressure sender for the hydraulic pressure. After the pressure module, the fluid goes out to the required services, and you can see pipes coming out of the left and right hand side of this, which go off all to the various services. Now, on the way to the services, there are hydraulic fuses, and you can see these in the wheel well. Now, a hydraulic fuse, if you're not familiar with the concept, we're probably all familiar with the concept of an electrical fuse. And if you think what an electrical fuse does, if there's too much current, the fuse burns out and stops the current flow. And a hydraulic fuse does exactly the same thing. So they're basically spring-loaded shuttle valves, and these will close the hydraulic line if they detect a sudden increase in flow, which you would get from a burst pipe or similar downstream. And that in these closing, it preserves the hydraulic fluid for the rest of the services. There are hydraulic fuses fitted to the brake system, and that's the ones I've shown here, just because they're the easiest to see in photograph. The leading edge flaps and slats extend and retract lines have all got them. Nose gear extend and retract lines, and the thrust reverser pressure and return lines. All of those services have all got hydraulic fuses on them, so if there's any damage either to the component or a burst in the pipe, you don't lose the whole system pressure. When the hydraulic fluid returns from the services, or the heat exchanger, if it's case drain fluid, it goes through the return filter for cleaning before going back into the reservoir. If the filter clogs, then a red differential pressure indicator will pop up, and you can see I've indicated where it is on the filter there. If the pressure differentials goes above 65 psi, the indicator will pop up. If it increases further to 100 psi, then a bypass valve opens and the fluid is allowed to go directly back into the reservoir, on the basis that even contaminated blocked fluid is better than none, if you know, at the cost of keeping your hydraulic system. On the photograph, you can see I've labelled the various parts. The bulk of this is at the bottom, the filter housing, and there's a clip just above it, a wire locked clip, so you can change that filter. The wire lockings become more and more intricate over the years, as a few of these have worn loose and been the source of loss of hydraulic fluid in flight. The return flow goes into the left. So that's where the fluid comes in from the services. It then passes around the outside of the case, is sort of squeezed in through the filter, and then passes up through the middle and back out for return to the reservoir. The heat exchanger fluid actually goes into the top, but doesn't go through the filter, surprisingly, even though it joins the filter cap. It just goes straight to the reservoir. If you're on a newer 737, anything within the last 5 years or so, you'll have a different coloured and a slightly different looking return filter. They've got a slightly different arrangement of the same pipes on top, so the return back to the reservoir is actually teed into the heat exchanger pipe up there. The differential pressure indicator is slightly different. So rather than the rubber cap, it's got that black thing. And a big difference is that the cap is now, or the filter housing is now on a ratchet lock, so there's even less chance of that coming in loose in flight. Alright, so let's kind of recap what we've done with all of those components and have a look at the flow, the hydraulic flow in the A system. So it all starts with the reservoir, which is pressurized from, well, the A system's pressurized from the left pneumatic duct, the B is obviously from the right pneumatic duct, and the reservoir obviously can be refilled with hydraulic fluid. From the reservoir there are two outputs, one to each pump. The engine driven pump though has a shut-off valve in between, which is operated by the engine number 1 fire switch. From the pumps, which are operated, as we know, on the hydraulic panel there, their output goes to the pressure module. The pressure module gives us information about the hydraulic pressure and will also trigger the low pressure lights. From the pressure module it goes to the services, and that's a list of services from the A system. Obviously in the B system that list would be different. After the services, the fluid goes back to the return filter, which we've just been looking at, for filtration, cleaning, and then is returned back to the A system reservoir. Now you recall that some of the fluid for the pumps is used for cooling. That goes away to the case drain filters. So those are small filters that you can see in the, well, you can see the electric one in the wheel well just below the electric pump. From the filters, the electric one's got an overheat sensor, which will also trigger the overheat light. From the filters they go to the heat exchanger in this case the number 1 main tank, and then back into the reservoir. So that's the flow of hydraulic fluid. The B system, very similar. The main difference is that it's got the PTU addition. So there's an extra pipe coming out of the bottom of the B reservoir, which goes to the PTU pump. PTU pump driven by a motor which is driven by the A system. The pump gives added pressure for the leading edge flaps and slats and auto slats. That fluid is then returned to the case drain filter and overheat sensor for the electric pump. So if by any chance the PTU pump were to overheat, that would show itself as an overheat light on the B system pump. The only other difference really is refills through the standby reservoir, and of course the services are all, well, it's a different list of services supplied. Alright, so let's have a look at the indications that we get in the flight deck and how they've changed over the years. So going right back to the originals again, you know, again, just for a historical record really to show you the derivation, and for those of us flying the NG or the Max, how lucky we are, you know, for having our nice ergonomic displays. In the originals there is only a quantity gauge for system A, and that's because A is if you recall, is the primary system, and the B system is filled from the A system reservoir. So system B quantity is monitored by an amber B low quantity light. The hydraulic system pressures are shown on one gauge with two needles, the A needle, as you can see, being at the front. And the hydraulic brake pressure gauge has also got two needles, And that's because on the originals, if you remember back to the landing gear module that I did, it's got two accumulators. System A does the inboard brakes and System B does the outboard brakes. Fast forwarding slightly to the early classics. Now these are the pre-EIS ones, so these were the classics built between 84 and 88. The B system on the classics now operates the trailing edge flaps. On the originals, the A system did both the flaps and the landing gear, but they've balanced the loads out now on with the classics, and the B does the flaps. So it's by way of promotion, it's now got its own quantity gauge, and the markings are a lot more simplified than they were on the originals. The hydraulic system pressure gauge, that's unchanged. It's still 1 gauge and 2 needles. The brake pressure gauge has changed because there's now only one brake accumulator, so it only needs to show 1 needle. So that's showing the brake pressure from System B. With the EIS classics, the display changed significantly. You've now got the quantity shown on an LED moving dot matrix. The pressures shown by the moving dot matrix. The quantity is a simple digital number, nice and easy, and the refill percentage, which is 88%, is marked there in small digits in blue in the middle. So quite an improvement, I think. Nowadays we've got this. The max display is above. That's on the lower DU, and on the max it's on the MDS, and it's very, very simple. It just shows quantity and pressure for A and B system. It's just a digit. If either system needs refilling, you'll get a white RF caption next to the quantity. So very simple. Notice the difference in quantities on the in-flight readings there on this max display. That's actually normal, and let me say a little bit more about that. So the table on the right there, this shows how the indicated hydraulic quantity, notice I've included the word indicated, because it's not the actual hydraulic quantity, but the indicated hydraulic quantity varies with configuration as the servicers use the fluid on the NG and the MAX. These figures are actually similar for all series of 737, but that one was compiled by Boeing for the NG in response to queries from crew about it. The indicated hydraulic quantity will also vary with temperature. So the refill figure, which is 76%, is only valid when the aircraft's on the ground, clean, with the engine shut down at normal temperatures. So, you know, if your aircraft's just landed, you know, and it's cold soaked off a long flight, and you're landing at a cold destination, you can see from that table the thermal contraction in the cruise is anywhere between 5 and 20%. So your indication on the ground will still be, you know, anywhere between 5 and 20% low. So the tendency could be for crew to report this, say, I'm below my minimum hydraulic quantity for dispatch. Get an engineer, he tops up the hydraulics, and next thing you've overfilled it as it warms up. But anyway, engineers should be aware of this. The one thing I draw attention to on this table is that trailing edge flaps have got no effect on hydraulic levels, and that's because they're driven by a hydraulic motor, not an actuator. And you can see that motor on the rear wall of the wheel well. All right, so on to services. For the A system, the services look like this. So top to bottom, you've got the PTU control valve and pressure for the PTU. This serves both the autoslat and leading edge devices. You got number one thrust reverser there, rudder ailerons, elevated and elevator feel, half the flight spoilers, autopilot A, alternate brakes, nose wheel steering, two-position tail skid if fitted, ground spoilers and landing gear. So quite a list. B system, a similarly long list. I think the significant thing here is the trailing edge flaps, which are on there. Well, this is a list, you can read at your leisure. It's in the FCOMs, so it's all there on the schematic. Standby. Now the services supplied here are the standby yaw damper, the rudder, numbers 1 and 2 thrust reversers, and the leading edge devices. Now the thrust reversers will operate slower than usual because remember the output pressure of this pump's only just over 3 gallons per minute, whereas it's 30 odd, 36 on the engine room pump. And the leading edge devices, this is for extension only. There's no facility for retraction of leading edge devices once you've extended them with the standby system. Now, while we're covering this, and I'm aware we're getting slightly off topic of hydraulics, but just for the sake of completeness, I'll mention that in alternate operation, the trailing edge flaps are moved with an electric motor rather than the normal hydraulic motor. And again, you can see that on the rear wall of the wheel well. But more of that in the flight controls video. All right, so a word about auto standby operation. We already know that we can activate the standby hydraulic pump with either flight control switches or the alternate flap switch by moving that to arm. But there's an auto standby facility as well. So it will operate automatically if either, and all of these conditions must be true, flight control A or B switches are on, so they're in the normal position. The alternate flap switch is off, again that's in its normal position. Trailing edge flaps are not up, so in other words you've got some flaps. The aircraft's in the air, wheel speed more than 60 knots, and you've got an A or B flight control pressure, a low A or B flight control pressure, or the main PCU force flight monitor trips. So that's auto standby operation. What it does is it activates the standby pump, it opens the rudder shut-off valve, it allows the standby system to power the rudder and the thrust reverser, and it brings on the standby rudder light. So the only thing it doesn't do on the standby system is the leading edge devices, because it has no effect over the standby leading edge device control valve. That is purely the domain of the alternate flap switch. So, summarising all that, because that's quite a lot of information. In plain English, if you're either airborne and you lose A or B hydraulics with some flaps, or the FFM activates, standby hydraulic pressure will automatically become available for the rudder and the thrust reversers. There you go. That's all you need to know. Right, redundancy. Let's have a look at that. So, putting together the A, B, and standby services, you get a picture like that. Now, again, I'm not going to go through this in minute detail. It's there for you to look at. If you want to study it, then just pause the video. But what I am going to say is, if you look at this, you'll see that most services have either got two hydraulic supplies, like the rudder PCU, the ailerons, the elevators, the elevator feel, the landing gear, even the autoslats and leading edge devices with the PTU, or they've got an alternate system. And an alternate system could be things like alternate brakes, um, or another autopilot, alternate nose wheel steering. So the level of redundancy here is very, very high. Let's take a closer look at it. So if we were to lose System A, this is what you would lose. And there's a list of in-op items there which I've just got straight from the QRH. Now, rather than go through that list in detail, let me boil it down for you to this. So, of significance, you've got no autoland because you've only got one autopilot. But you know, big deal. I mean, that we probably only need autoland about 1 in every 100 flights. Roll rate and speed brake effectiveness is reduced slightly. Now, I've flown the aircraft with only half the hydraulics, and I promise you, you won't notice it, or you won't easily notice it. It's not going to be a big issue. Next item, manual gear extension needed, retraction not possible. This is the biggie. This is the only item of any real significance in my book with loss of System A. Not only do you have to do a manual gear extension and give yourself time to do that, retraction is not possible. So you have to seriously think about where you're going and your plan B if you don't get into that airfield, because diversion fuel will be an issue with the gear down. Other items on the list: no ground spoilers, so landing distance will be increased. Now, the increase in landing distance, it's only a couple of 100 meters. You know, it's really not a lot. And the engine one thrust reverser will deploy and retract at a slower rate. Again, this is one of those things that you won't really notice. It's not a significant effect. Loss of System B, that's what it looks like. That's the list of in-op items as taken from the QRH. Again, go through that at your leisure. Pause the video if you need to. But what I'm going to do now is I'm just going to boil that down to the significant items. So, again, no autoland. Roll rate and speed brake effectiveness reduced slightly. Who cares? No yaw damper. Again, this is something you probably will not notice. I mean, I've flown the 737 many times on revenue flights with no yaw damper, and you might just get one of the cabin crew at the back calling up, feeling a little bit queasy because of a little bit of sort of wobbling, particularly in the long body aircraft, you know, the 48900s. But really, it's hardly noticeable. I've on air test, what one of the things we do is we switch off the yaw damper and put in a rudder doublet to just set up an oscillation, and the aircraft will stabilize within one oscillation when you switch the yaw damper on. Now, out of interest and curiosity, I left it without switching the yaw damper on once, just to see how many cycles it would take, and it was about 3 or 4. It's incredibly longitudinally stable, the 737. It will damp itself out very, very nicely. So the bottom line is, and what I'm saying is, you will hardly notice that there being no yaw damper. The biggie is the trailing edge flaps. You will have to extend the trailing edge flaps with the alternate electrical system, and for that reason, you should, as directed by the QRH, of course, do a flap 15 landing, and that's because for the go around, if you've got any more than flap 15, your go around climb performance will be severely compromised. Landing distance will be increased, of course, because it's a flap 15 landing, but the VREF will be higher. The other thing to note is that with the leading edge devices, you can extend them with the standby system, but once extended, they can't be retracted. So again, think fuel consumption, think plan B, think think of your alternate. Use manual braking, yeah, and because there's no auto brake available, and again, engine number 2 thrust reverser will be slow. So again, for me, it's all about the flap 15 landing one, the electrical system, which will take a bit of time to do, and if you need to go around and or divert, the leading edge devices will be stuck out. Okay, onto the power transfer unit now. We've mentioned this before, but let me just round this off by, well, for a start, showing you where it is. That's the wheel well of an NG, and in the red circle, that is the power transfer unit. It operates automatically to operate the order slats and leading edge flaps and slats at the normal rate. That's the point. If system B, engine driven pump pressure, is lost. And the criteria for this is that for most aircraft it's with the flaps anywhere between 1 and 10. But on some aircraft, and this is the SFP aircraft, the short field performance ones, if the flaps are not up, because on those aircraft you can take off with flaps up to 25, and you're airborne. So you can see on the PTU here, if I just label it up for you, it's a hydraulic motor which is driven by system A hydraulic pressure, and the motor is on this side of the picture, and you've got your hydraulic A lines going, flow and return going in and out of the motor, and that motor is on a common shaft to a hydraulic pump, to a pump which powers the B system through it, and the pump's on the other side. And again, you can just about see on the far side the B system flow and return lines from that. So what this is doing, it is pressurizing that B system fluid using the A system motor. Now that pump, it's about 11.5 gallons per minute, so it's twice the capacity of the electric pump, and that's the point. What we're trying to do here is or what Boeing are trying to do is give you the PTU and the autoslat at the normal rate, because with the engine-driven pump gone, for to rely on the electric pump, they would only operate quite slowly. So this gives you the required speed for them to operate, for you to operate safely. One other detail to mention is that if the PTU should overheat, then the B system electric pump overheat light will illuminate. That's because the PTU fluid is returned through the B system overheat module and case drain filter. So yeah, the other component is the landing gear transfer unit, and this is on the keel beam ahead or forward of the PTU. You can see I've marked it there in the red circle. I'll just zoom in on that now, give you a close-up of it. There it is. Now this is similar but different to the PTU, but working in the other sense. So the LGTU allows system B to retract the landing gear if the engine 1 falls below 50% N2 on the NGs or 56% N2 on the classics. In other words, if that engine fails. Without the LGTU, gear retraction would be very much slower, because you don't have the engine driven pump, you've only got the electric pump, and that, I mean, it will be indeterminately slow, and that would compromise your engine out performance. So this is to retract the gear after takeoff. That's what it's for. If you lose engine 1 on takeoff, you can still retract the gear at the normal rate. That's what this is doing for you. Now the LGTU logic, coming from the N2 gauge of engine 1, that's the reason that dispatch is not permissible on the classics with the engine 1 and 2 Taco US. there's actually no alleviation for the NG and the Max, so both tachos have to be working. But on the classics, you could dispatch with the N2, sorry, the engine 2 N2 tacho US, but not the engine 1, and this was why. It was a pain. I only ever had to do it once, and there were a lot of issues, like, for instance, with engine starting and start cutout, but I digress. The original series don't have an LGTU. So, to conclude, hydraulics. It isn't actually that difficult. The schematic looks horrendous, but that's only because there's a lot of it. It's very simple when you break it down into its component parts. Take a bit of time, study the schematics, either this one or the one in your FCOMs or any third-party ones. As I say, they all work the same. But once you understand the flow of it, it really is quite straightforward. So, as always, that's it from me. Please, if you've enjoyed this video, if you found it useful, give it a like, subscribe to my channel if you haven't already done so, and share it amongst your friends. Thanks very much for your time.